All right, guys, 3, 2, and 1. Guys, in this particular video, we're going to talk about vertical stretches or compressions. And so in order for us to either vertically stretch or compress a square root function, we have to multiply the square root function by some constant. But when I do this multiplication, it doesn't happen inside the square root. It happens outside the square root. So when I do it, it looks something like this. This is an example of a square root function that has either a vertical stretch or compression. That's my k times the square root of x. And then this number here, this constant k, is the number by which I'm either vertically compressing or stretching the function. Now, the nice thing about vertical stretches and compressions is that their rules work a little more intuitively than the rules for horizontal stretches and compression. You'll remember from horizontal stretches and compressions that they are opposite of what you would think they are. I'd have to be multiplying by a reciprocal if I wanted to stretch, and if I wanted to compress, I would multiply just by the regular constant. Well, this doesn't work like this. This works the way you would think it would work. So if my k is greater than 1, the graph of k of x is vertically stretched. And what that means is the vertical distance from the x-axis is increased. And if my k is less than 1, the graph of k of x is vertically compressed. That means the vertical distance from the x-axis is decreased. And so when k is greater than 1, you would think that the function is getting larger. When k is less than 1, it's like it's getting smaller. And so let's take a couple of look at some examples here. Of course, I have my parent function f of x equals the square root of x. Now, if I want to stretch this graph vertically by a factor of 2 units, that would end up looking something like this. So now the blue graph is the red graph when it's stretched vertically by a factor of 2 units. And what that looks like, the shape looks basically the same as the parent function, but it's stretched a little bit. So it doesn't look exactly like the parent function, but it has the same general shape. And you will see that my blue function is the same as the red function, but it's that arrow is kind of letting you know you're stretching it vertically by that factor. And of course, the equation has the 2 that's outside of the square root. So that's what a vertical stretch looks like by a factor of 2. Now, when I do a vertical compression, of course, I have my parent function that looks like this. But if I want to do my vertical compress it by a factor of 2, it looks like this. So notice now the blue, same general shape, but it looks a little smaller. It's compressed. It's closer to the x-axis. And so it's moving down. So the blue graph has the same general shape as the red graph, but now it's been compressed vertically by a factor of 2. And so whenever I want to do a compression, vertical compression, I multiply by the reciprocal of the factor that I'm compressing by. So in this case, since I'm vertically compressing by a factor of 2, I'm multiplying the whole square root of x by the reciprocal of 2, which is 1/2. And that's why it looks the way it does. And so vertical compressions and vertical stretches are a little more intuitive, easier to understand than the horizontal stretches and compressions.